Let's talk about adding vectors. We're going to start with some simpler problems. And keep in mind, right now we're working with displacement. However, all vectors add the same. So whether you're adding velocities or accelerations or forces or field strengths, it's all identical. You can always pretend it's displacement, so you get the benefit of your intuition for how displacement works. So first question, if you walk 3 meters south and then 4 meters south, how far are you from where you started and in what direction? You will be, unsurprisingly, 7 meters south of where you started. If you walk 3 meters south and then 4 meters north, you're just going to be 1 meter north from where you started. This is kind of like your resultant vector right here, from your first tail to your last tip of the arrow. So 1 meter. Then we get a little more complicated. If we go 4 meters east and then 3 meters north, we just draw our vectors in, and it doesn't matter what order we draw them in. Either way, we'll get the same vector if we draw them tip to tail. So we walk 4 meters, then 3, and keep in mind we could get to exactly the same point here if we decide to walk 3 meters north and then, oh crud, I'm doing this backwards. If we do 4 meters east and then 3 meters south. Then we can find this guy with Pythagoras, our resultant vector. Our maybe I should draw this in a different color. So here is our total displacement. We walked 4 meters east and then 3 meters south, and we end up this distance and in this direction from where we started. This is our start here. So let's calculate this. So if we want to find that, it's just Pythagoras. X equals the square root of a squared plus b squared, 4 squared plus 3 squared. So that will be 5. So here we've got a side of 5. And a lot of times with these questions, it's good to know the angle. In what direction were you moving? Or in what direction are you from where you started? So in this case, you can use sine, cosine, or tan because we've got a nice right angle triangle here. I'm going to use tan just for fun. So if I want to find this theta here, I'm going to say theta is equal to the inverse tangent of 3 over 4, the opposite over adjacent, which happens to be, just quickly peeking, at my answer key. We do that, it happens to be 37 degrees south of east. So, one, note this angle is touching the east line. Line is pointing east. So I would say my displacement is 5 meters, 37 degrees south of the east line. Notice my second thing I mentioned is east because it is touching that east line. It's not touching the south line, it's touching the east line. Now you could also report this blue vector here with this angle, if you found that, and that is just fine. That would just be east of south because this angle right here would be touching the south line and is east of it. So let's look at the next question. Pretty much exactly the same idea. So we go 8 meters east and then 5 meters north. And then we just want to find that using Pythagoras. Maybe we'll use the other color to show that it is the resultant going from where we started to our final point. So this is our total displacement if we walk 8 meters west and then 5 meters north. To find this number, we can use Pythagoras again. So we'll call it x or whatever. find theta. X is equal to the square root of 8 squared plus 5 squared, which would put it roughly around 9. And our theta is just going to be the inverse tan of opposite over adjacent. Inverse tan is just a button on your calculator. Tan converts from like an angle to a ratio. So that goes angle to like side ratio, which in this case is 5 over 8. Inverse tan does the opposite. It goes from side ratio, which we know, to the angle itself. So these are just two buttons on your calculator. If you've got the side ratio and want the angle, use inverse tan. If you've got the angle and want the side ratio to solve for another side or something, use tan. And same thing with the other trigonometric functions. Anyway, whatever these guys are, I'll peek at my answer key. It looks like 9.4 and 32 is what our calculators will give us. So 9.4 meters, we end up 9.4 meters, 32 degrees north of west. And I'm saying north of west because it is touching the west line. This angle is. Another way I could report the direction of this blue vector is if I give its angle relative to the north line, and in that case it would just be west of the north line. Whichever like axis it's touching is just what you report second. Like the angle we got is north of the west line. If I wanted this angle, it would be west of the north line. So hopefully that makes sense. Anyway, your full answer is 9.4 meters, 32 degrees north of west. I'll save these guys for you to figure out because they work exactly the same, and hopefully that made sense. And we'll just go over 7 and 8. So these are a little bit different. This whole hint add collinear vectors first sounds super fancy, but really it's just saying, hey, if you got some vector to the south and some vector to the north, let's deal with that first because we know how to deal with that. That is super easy, either addition if they're in the same direction or subtraction if they're in the opposite direction. And then we can just take our total north-south and combine it with our total east-west. Or total east-west and combine it with our north-south, if depending on our situation. So in this case, right now we've got 7 meters south and 8 meters north, leading to a total north-south of 1 meter from where we started to where we ended up. And we also go 6 meters east. So I'm going to start with my east vector just for fun, because I like doing north and south of east, just for convention's sake. But it works equally well starting with the 1. Make my little right angle triangle. I guess I'll use my blue to show you it's the resultant. Now, if we want to find this guy, again, as usual, same business as always. We want to find that guy. We'd also like to find our angle. So same business as normal, Pythagoras. 1 squared plus 6 squared square rooted gives us x. And our theta is just equal to our inverse tan because we've got the ratio and we want the angle. Our ratio is opposite over adjacent. So this is opposite the angle. This is adjacent over the angle. Now it's going to equal what it equals. I'll go look at my lovely answer key. Looks like 6.1 meters, 9.5 degrees north of east. So we'll just 6.1 meters, and what was it, 9.5 degrees north of east. And then we can put them together for our final answer. 6.1 meters. We are 6.1 meters from where we started in the direction of 9.5 degrees north of east. Now, if we want to do this guy, exactly the same. We've got an east-west thing we're going to deal with first. We go 20 meters east and then 15 meters west. And our total displacement from where we started in the east-west axis would be 5 meters to the east. And so then we'll combine our total north-south with our total east-west. We are 5 meters east and 12 meters north. Bigger angle than we're used to. So we'll find this guy, we'll find theta. Oh, maybe I'll do my other color just to show it's the resultant, not the vectors we're adding on our resultant vector. And aside from that, we just do the same thing as normal. Tangent or some other trigonometric ratio if you want, and Pythagoras. 5 squared plus 12 squared. This is a perfect one. This will end up being 13, I think. Yes, that would equal 13. And then our theta is the inverse tan of 12 over 5, which I do not know offhand, so I will look that up. And that is 67 degrees. And this is north of the east line. Notice it is touching the east line and north of it. Again, if you drew your triangle differently, you might be reporting whatever this angle is. I guess 23 degrees east of north. So put them together, we got 13 meters at 67 degrees north of east. And that is how you add vectors. And keep in mind, it works just as well for forces if we change meters for newtons. It'll work for magnetic field strengths if we replace meters for Teslas. So use your intuition you have for displacement and apply it to all vectors ever. Enjoy. Thanks for listening.